Okay, so welcome you all in the sixth Gauge Gravity by the Ghat seminar series. And our today's speaker is Karthik Prabhu from Raman Research Institute. He has recently joined in RRI last year. He did his PhD from University of Chicago under Professor Wald, and he has been a postdoc at Cornell and UCSB. He works largely on classical and quantum aspects of gravity and field theory, and he will be talking to us about infrared finite scattering in QFT and quantum gravity. So let's welcome Karthik.
Thank you. Thank you for having me. And yes, I will be talking about the paper Infrared Finite Scattering in Quantum Field Theory and Quantum Gravity. This is joint work with Gautam Satish Chandran and Robert Wald. If you want to find the paper, it's the same title, so hopefully you can find it. Okay, so what's the problem? Okay, so what we want to consider is some scattering process of particles or fields. And by scattering, we're idealizing something where we're going to send in something from past infinity and let it interact, do whatever, and then see what comes out at future infinity. So going to infinity is this idealization. So all the interactions happen at finite time, and then we see what shows up in the far future. So there's kind of this is a conformal diagram, but just to explain what this is this is kind of an asymptotically flat space-time, and you can attach boundaries at infinity, which is convenient. You bring infinity down to a finite place to study things there. The thing that looks like a point here, I minus and I plus, are sort of infinities along time-like directions. So massive fields and particles will go to I minus and I plus. But these lines at 45 degrees are null infinities. So that's where null geodesics or null directions go to infinity. For example, massless particles like photons and stuff will all reach these 45-degree lines instead of going to this I plus and I minus. And here I've sort of drawn a cartoon picture of sending something in from past time like infinity. So this can be a massive field or a massive particles like electrons or something. And you send, let's say, two of them in. And in the space-time, they do something complicated. They spiral around each other, interact with each other in really complicated ways. But in this process, because they're interacting, they also emit radiation depending on what they're coupled to. So if these were electrons, this radiation would be sort of electromagnetic radiations. So electrons jiggling around each other will just produce photons or electromagnetic waves that reach null infinity here. Or you can think of these as massive particles or, two ginormous planets or stars spiraling around each other before they collapse or something to produce gravitational waves. So this is just classical right now. So even in the classical theory, if you look at this radiation field, and there's a time parameter, which is u, which is the retarded time parameter. So I should mention that there are a bunch of directions suppressed. So this thing that looks like a 45-degree line is actually a line, but each point on it is a two-sphere, so denoting different angles that the radiation can go out to. But in any case, this u is a time parameter along a genuine line. And if you ask, for example, let's do electromagnetism, and let's look at the vector potential on this surface. So this radiation actually falls off as 1 over distance from all these sources. And this vector potential is the leading order part, so 1 over r part of this vector potential, say. And you ask, okay, how does it look if I scan it along this u direction? So this is kind of a cartoon waveform. It shouldn't be taken as real data. And so what happens is, suppose it starts at some value. it can be zero or non-zero. It doesn't really matter. And then its amplitude kind of wiggles around as radiation is emitted. And then it settles down to a constant value. This is really, really far off at sort of u tends to infinity. It settles down to a value which wasn't the value that it started with. And this effect classically is called the memory effect. There's an analog in the gravitational case where you look at the gravitational waveform and you similarly expect that after all the gravitational waves have passed, long time after they have passed, the value of the field doesn't return back to its original value. So in gravity, this was first called the memory effect in gravity because if you imagine this waveform as being, some LIGO detectors floating around, what this says is your LIGO detectors are sort of permanently displaced relative to where they started before the waveform started to appear. So the gravitational wave somehow remembers that that a gravitational wave passed by. So it's called a memory effect. And this is very exaggerated in this cartoon picture. Usually this delta is really, really small. So if you started at zero, this value would actually be really, really tiny. Okay, so, and this memory effect will be crucial to everything I'll be saying. So we should keep in mind this permanent displacement of what's going on. And don't worry about the other formulae. I'll kind of repeat them later on. Okay, so now let's actually see everything I told you I've kind of written in equations. So what we're going to try is just look at a simple case. We're going to send in some massive scalar field, which is charged. So it's coupled to electromagnetism. So these are kind of toy models of electrons and positrons, but without spin. So you model them as scalar fields instead of fermions. You can do this with fermions too. There's no actual obstruction. It's just you have to keep track of fermionic variables, which is not relevant really to the problem. So you ask, okay, what does this scalar field look like in the limit to I plus minus? Remember, I plus minus was the far past and the far future for massive fields. And there you can describe this by, what looks like usual creation annihilation fields. So these are still classical fields, not operators, just by Fourier transforming, where P is kind of the momentum of the field that you're sending in. And you ask, okay, what does the electromagnetic field look like at early and late times, but in null directions, so near null infinities? And if you actually do this for electromagnetism correctly, there actually is a leading order part. What I said that it goes as 1 over r was actually for gravity. That was my mistake. And this leading order part has a time derivative, which literally is the electric field, how much electric field is radiated away. And this electric field is the radiative field. It measures how much electromagnetic radiation shows up. And again, there are analogs for this in gravity, where the analog of the electric field is the Muse tensor, which measures energy carried away by gravitational fields and so on. We'll see that later on. These indices, capital AB, are indices only along the angular directions, not in the time directions. Or another way of thinking about this is this index takes two values. So it's on an index on a sphere, tensor index on a sphere. So it takes two values. And those two values can be viewed as sort of polarizations of the electric field. There's a precise way to do it, but roughly that's what it means. And the electromagnetic memory, so this difference between the late time behavior and the early time behavior of this vector potential is just given by the integral of this electric field. So something like this. Okay, so now what happens when we go to quantum fields? So what we're going to do is we're going to take all these fields that we had, so the electric field, the massive field, creation, annihilation kind of fields, and promote them to operator valued distributions in the quantum theory. So that's our quantization. So when it's an operator valued thing, I'm going to write it by a boldface, so it's clear. And distribution just means that quantum fields are actually singular, so they don't actually have a value at a given point. What you should be doing is sort of smearing this in with test functions. So think something, an example of a distribution is a delta function. So you can't define its value at 0, but if you smear it with a smooth function, you get a number. So it's a quantity of that kind. And it turns out you can build an entire quantum theory starting from this operator. The massive case I'm not doing because that just gives you the standard theory. All the weird stuff happens in the massless field, which in this case is electromagnetism. So there is a Poincare invariant vacuum state, which is basically defined by its 2-point function in the electric field being, this quantity. The details of this formula really aren't important, but the important thing to note is this actually is Poincare invariant. It actually is also BMS invariant or something, but we'll get to that later on. Okay, so now we have the vacuum. How do we build the one photon states? Well, you take this guy and its corresponding creation annihilation operator. And remember, this was a distribution, so you can smear it with some test function. So these are smooth functions with compact support, let's say. So wave packets. And it turns out, if you go through the algebra, which I've skipped here, the norm on these kinds of wave packets has some formula like this, where I Fourier transformed this in U. So if you do a Fourier transform in U, you get a frequency, which I'm calling omega, and the angles remain the same. So there's an integral over the angles of the square of the function, which is not a problem. In frequency, you get an integral from, all over positive frequencies of, d omega is just the measure, but you get a frequency times square of the function. Now, this norm has an interesting consequence. So if your wave function had a memory, so if this S started at some value at minus infinity and went to some other value at plus infinity in U, if you Fourier transform a function like that, you get this memory divided by the frequency. So that's because the field doesn't decay back to 0. You get a 1 over frequency in its Fourier decomposition. What that means is if you try to calculate the norm of something that has non-zero deltas, this memory, you get a d omega divided by omega. So this 1 over omega gets squared, and you get d omega divided by omega, which is logarithmically divergent near 0 frequencies. And so this norm will not be finite. So what this means is there are no states with memory in the standard Fock space. So this entire construction reproduces standard quantum field theory's Fock space. But there is no state with this memory effect in this Fock space. But as I mentioned before, we do expect, even classically it is known that you will get memory in any non-trivial scattering process. But when you go to the quantum theory, if you stick to the standard Fock space construction, you're not allowed any of those states in your Hilbert space. And this is a problem because in scattering theory, you generically expect to produce these states, even in the quantum field theory. So we need to construct states with memory, and which do not lie in the standard Fock space. And this was done a long time ago by Abhay Ashtekar. And the way to do it is you pick a classical state. So recall, this is not, hopefully it's clear that this script E is not bold-faced. So it's a classical electric field, which has non-zero memory. So remember, the memory was given by the integral of this thing. So for example, if you pick a Gaussian, you'll get some non-zero memory, for example. And then you shift all your operators by this classical solution times the identity operator. And because you're shifting by an identity which commutes with everything, all the commutation relations are preserved. So this is an automorphism of the operator algebra. And then, because now you've added in this classical memory, any construction you do with these shifted operators gives you a new Hilbert space, which has this memory that you started with. So you could have started by choosing the script E to be any memory you want, and you'll get a whole Hilbert space of states with that memory. And so you can say, okay, if I construct two of them, so one with memory delta, one with delta prime, they're unitarily equivalent. So in Hilbert space sense, unitarily equivalent just means there's a unitary operator that maps one to the other. But they're unitarily equivalent if and only if the memories are equal. And recall here that I'm not saying the memory as some number. The memory as a tensor, which is a function of angles, has to be equal. So you get infinitely many Hilbert spaces, each labeled by a tensor that you pick. And there are uncountably many inequivalent Hilbert spaces. So, okay, we saw that the Fock space was a problem. So we wanted to construct states with memory, and we got a whole bunch of Hilbert spaces with some memory value. Okay, now can we do scattering? Not really, it's not that trivial. So because you have so many states, you have to actually, writing an S matrix is a problem because the S matrix is supposed to be an operator between Hilbert spaces. And now you have a lot of these Hilbert spaces, not just one. So for example, the simplest, and this is the most boring case, if you had no sources and just pure electromagnetic radiation, then you can show that if you send in a state with memory, so in means from past infinity, and then it interacts and becomes out at future infinity, then the memories are related by what's called an antipodal map on the sphere. So you take a sphere and you map one point to its completely opposite point through the center. So that's the antipodal map. And I'll explain kind of where this relation comes from. So this is the trivial case where if you know the in memory, you already know the out memory. So the in memory you can take to be zero. It doesn't matter. It's just that these two are equal. The equality is key, not what you pick for the in memory. And so what this means is if you start in some Fock space labeled by this memory, you already know before doing any scattering calculation which out memory you're going to. And so you can write down an S matrix between Fock spaces labeled by these memories. But this is the trivial case. There's no interaction. Even if you write down the S matrix, it'll just be kind of the identity matrix. There's no actual interactions going on. And you can say, okay, let's add sources. So a simple case you can do is you can add a classical source. So you can say, I'm treating my electromagnetism, so photons, quantum mechanically, but I'm treating all the sources like electrons and positrons and all these charged particles classically. Then there's an extra term in this equality, which is, given by the classical current term. It isn't exactly the classical current term, but it's some formula in terms of the classical current. In this case, also you can write down an S matrix because you fixed the classical current. So again, given an in memory, you add that classical current term that you picked, and you'll find out what the out memory is. And in this case, you can write down an S matrix, and it will be non-trivial. But now, if you want to do a fully interacting quantum theory, and your source is also a quantum field, what happens is your current term is not of some definite value. So quantum fields have all these fluctuations. So you cannot assign a definite value to this current term. So if you start with a fixed in memory, let's say 0, the quantum fluctuating current will produce a fluctuating out memory. So your out memory won't have a definite value. So it's not restricted to one of these Fock spaces that you constructed. It will be spread out over all of them. And you don't know a priori which ones it is spread out over, because if you do the full interacting problem. And all of this I've sort of mentioned in a very different language. But this problem is well known, and it shows up in standard QFT books in the sense that if you just pretend that all the states you get are in the standard Fock space, so the standard Fock space had no memory, so the subscript is 0, then you can show using standard QFT S matrix calculations that the S matrix diverges at low frequencies, and this is called the Weinberg-Soft theorem. And the S matrix diverges really because you're assuming this thing which is false, that your scattering should map you between the same Fock space. So the in and out Fock space are the same thing.
So let me ask a quick question just to make sure I understand.
Yeah.
So this, so here it seems like, wouldn't it be more natural to match at the level of charges than at the level of memory? Like here, your calculation looks like, it looks like you're trying to match at the level of currents. That's roughly instead of, I think it would be, if you're matching at the level of charges, wouldn't it be, it seems more physically plausible.
Yeah, I'm getting to that. That's the last line on the slide.
Oh, I see. Okay. Yeah.
Yeah.
Okay.
I'll get to that.
But these charges would ultimately actually also be angle dependent, right?
Yes.
Okay.
Yeah. Are there any other questions?
Let me ask one more question. It's in the previous slide, you had an omega and an omega naught. The omega naught was basically just the vacuum, right? It was just, I think it was notationally the same thing. So just to make sure I understood what was going on.
Sorry. Yeah. Here, omega naught is the vacuum state.
Okay. Yeah.
But here, omega is the frequency. I mean, it's kind of unfortunate that they're used, but I think from the context, it should be.
Yeah, it was clear. I just wanted to make sure.
Yeah. And I'll make sure to distinguish between them if they show up again. Thanks. Okay, so as Chetan was saying, the problem in this whole story is that the memory is not conserved, except in this stupid trivial case. So what we should be doing is that we should be building Hilbert spaces using conserved quantities. So anything you send in, you will get the same value out and not the memory. And that's the next part I'm going to get to. So this is just a summary, and I'll pause again quickly for a minute if people have any questions about this part. Okay, conserved quantities. What do we do with them, and what are they to start with? Okay, so a prototypical conserved quantity in electromagnetism that you should have in your mind is the total charge. We know that the total charge is conserved. But there's a whole long story about asymptotic symmetries and all that stuff. But what turns out is there is a whole angle's worth of charges which are defined at spatial infinity. So this is, if you go far away in radius, in distance from all these sources, but at fixed time, you will reach spatial infinity, but you'll still have a dependence on the angle. And so there's a charge value for each angle. So if you decompose this into spherical harmonics, the L equals 0 part is the total charge that we usually think of. And how is this charge defined at spatial infinity related to all the stuff going on at these boundaries? So it's related by a charge formula at I minus. So remember, I minus and the same at I plus was where we collected all our electrons and positrons, all our massive fields. So this is just a charge formula that's determined completely by what the massive fields you're sending in. But if you have radiation, in particular, memory, radiation with memory, you get a divergence of the memory tensor. So given the charged particles, say at I minus, and given some radiation, say along past null infinity, here I haven't drawn the past null infinity directions, but you can imagine sending in, electron, positron, but then also some photons. So there'll be some cartoon arrows going in. And if that has memory, you'll get this. And there's a similar formula relating charge at this vertex to the memory through this to the charge at I0. Now, this charge at spatial infinity is conserved. So whatever charge you send in is matched in the charge out with this antipodal map on the sphere. And this was conjectured by Strominger a long time ago, and now it's been proven in many different contexts. So as Chetan was suggesting, okay, now we have a genuine conservation law, which doesn't depend on whether you have memory or not. So we should instead try to build Hilbert spaces which have a definite value of the charge. So if you send in some charge, you know which Hilbert space you're in. And then you automatically know by this conservation law that which out Hilbert space it will go into. Okay, so let's try to do that. Let's try to see how far we get with constructing these Hilbert spaces. Okay, so this is kind of a dense slide, so I'll go through it slowly. So this construction is the Faddeev-Kulish construction, which was also done a long time ago. And this is I'm currently mentioning it only for massive sources. So your electron and positrons are all massive. There are no massless particles except for photons, which don't have any charge. Okay, so what do? You do the following construction. You start with some number of particles with momenta P1 through Pn and antiparticles with momentum Q1 through Qn. The ends are the same here because I'm doing a special case of zero charge, but I'll mention that you can put any number of each of these. And that gives you some state, which is like a momentum state. So one thing we should remember about these guys is they're improper states in the sense that they're a basis of your Hilbert space, but they're not actual states. They're not finite norm states. So you have to smear these around to get wave packets, but that'll happen later. And if you send in these guys, you can compute the charge that you're sending in from past infinity, just for the massive fields. And it's just the sum of Coulomb charges. So each of these will have some Coulomb charge when they're at rest. So you boost them to whatever momentum they're supposed to be, you can boost the charge and you'll get some formula for it. How the formula looks is not important except in one place, and I'll mention what that place is. Okay. Now this thing has non-zero charge. So let's suppose we want to construct a Hilbert space where the charge at spatial infinity is zero. I've just picked zero here just to make the presentation easy, but this can be whatever fixed value of charge at spatial infinity that you want as a function of angles. So we need to cancel out these charges. So what do? We send in a bunch of photons whose memory is chosen so that this equation is satisfied. So 0 equals, this formula is given in terms of the momenta. And so you want to solve for this tensor delta, this equation, in terms of P's and Q's. And then what you do is you construct what's called a dressed state. So you take a bunch of these particles, antiparticles, and you take these bunch of photons with a very carefully chosen memory obtained by solving these equations. And you construct sort of a joint state, and then you smear in the momenta to get an actual state. So all of these kinds of states have zero charge at spatial infinity just by construction of how we chose the memory. Here I want to point out that if you fix the momenta, P's and Q's, the psi is not fixed. Only the memory of the psi is fixed. So the psi can be any electromagnetic state with this memory. And there are many of them. There's no unique one. And this construction is called the Faddeev-Kulish Hilbert space. Basically, you start with something like this, and you sum over all possible particle-antiparticle number, still satisfying this equation for each of them.
Sorry,
And then, yes,
just a quick question. So F delta is your Fock space with delta memory.
correct.
Is that okay? All right, thanks.
Yeah. The delta label really is a tensor, but I've just written it as a symbol.
Right, but it symbolizes the fact that you have a single
8-bit
memory.
memory. Yes.
Yeah.
So is there any some constraint on the energy of the photon that is carrying the memory?
No. You can make it as big as you want, as small as you want.
So in effect, you're changing your scattering problem, is it?
Yes, that is the point I will get to. That if you want to follow this construction, you're kind of changing the problem and saying that you've solved it. I mean, I'll mention that in a little bit.
Okay.
Okay, and now here you can write down an S matrix because your charge is conserved. So if you start in this Faddeev-Coolidge-Hilbert space, you will always end up in the Faddeev-Coolidge-Hilbert space of the same charge value, which here I've put to 0. Okay, so this is all nice. You get back your S matrix, hooray. There's a bunch of problems here. So remember that the Coulomb charge cannot be dressed away. And that's because this memory, which has one index as a tensor field, is always supported on L greater than equal to 1 harmonics. So there's no constant tensor field with one index on a sphere. So there's no L equals 0 part. So at least from the previous slide, and this was the original Faddeev-Coolidge construction, was that you need to send an equal number of particles and antiparticles. So as it was mentioned, that you're kind of changing your scattering problem. If your experimentalist friend comes in and says, hey, I want to send in 2 electrons. Can you tell me what the S matrix is? You go back to your office and you secretly hide antiparticles somewhere in the problem, do the calculation, and then go tell your experimentalist friend the answer. They don't know that you've hidden all these antiparticles in your Faddeev-Coolidge-Hilbert space. And usually this goes by you have to hide particles behind the moon. I mean, you don't really have to do it behind the moon. You can put them in your back pocket and not tell anybody. But it is changing what the original scattering problem your experimentalist friend gave you. But that's just because you want to do scattering in this Faddeev-Coolidge-Hilbert space. The other problem, and this problem can be, as I was mentioning during the previous slide, this is not really a problem. You can do the Faddeev-Coolidge construction with any value of the total charge, the L equals 0 harmonic of the charge. It just wasn't how it was done in Faddeev-Coolidge, but that's an easy problem to fix. Now, the problem with fixing this is that if your charge value is not 0, remember this is a function on a sphere now, not just the total charge, that is not Lorentz invariant because it's a function on an angle, and when you do, when you rotate it or even Lorentz boost it or something, the value of the charge will start changing. So your Faddeev-Coolidge-Hilbert space is not Lorentz invariant unless the charge value is 0. Which means that
Karthik, Sumati has a question.
Sorry.
Yeah.
Can you explain that a little bit? Why do you say it's not Lorentz invariant? Is it because of the theta dependence of theta phi dependence of?
Yeah. So
it just means technically, where is it? Where is this Lorentz invariance broken?
Okay. Yeah. So the Lorentz boost part is kind of hidden in what's going on, but let's just look at rotations, right? So if I give you a random function on a sphere, it's not rotationally invariant unless it's a constant.
Right. So that comes in to the definition of the charge itself, is it? The fact that these charges are theta phi dependent?
Correct. Yes.
Is it just that? Okay. All right.
It's just that. So,
okay,
I mean...
okay, fine. Thanks.
Yeah. In the electromagnetic case, sort of one way to see this is, usually this charge is the limit of FTR, so the T radial component of the electromagnetic field, right?
Mm-hmm.
That can depend on angle.
Right. And I
Usually
guess
we
the
only
point is
take the
that
constant.
the zeroth moment or whatever, you know, the first thing is, of course, is uniform. It's not theta phi dependent. That's a standard charge. But then we have these
Correct.
additional sets of charges that are,
Yes.
which one is sort of allowing or thinks of allowing in the theory, right? I mean, so yeah.
Correct. Okay. So coming back to that point, that relates to Lorentz boosts, is that these charges are not really functions. They're conformally weighted functions. So they also transform non-trivially if you do a Lorentz boost. They get multiplied by some boost factor, the Lorentz boost factor kind of thing. So even if you start with something that had, let's say, only the constant piece and no angular dependence, right? If you boost it, it'll pick up angular dependence. And this can be seen by just consider a static point charge that'll have a, on a sphere that'll have a constant charge, not angularly dependent, right? But if you Lorentz boost that particle, you're boosting it in some direction, and that'll pick up higher harmonics.
Right. I guess the point is, because this is at I0, right? I mean, there's some choice of, I mean, I don't quite see it exactly, but I mean, I0 is a very special point on the boundary, or the region of the boundary, but, is it coming from the fact that one has a spatial slice, that one, of course, when one is looking at something on a spatial slice, the question is, what does a boost do to that?
Correct. Yes.
That's similar to that.
Yeah.
I see. Okay. Thanks. Yeah.
Yeah. And I mean, you can think of this in either way, is you're either boosting your spatial slice, or you can think of it as boosting your fields around, but on the same spatial slice, right? And they basically do the same thing. And yeah, you get this angular dependence.
Right. Okay. Thanks. Yeah.
Yeah. So because this charge is not Lorentz invariant, the Hilbert space constructed with the original charge value that we started with, and then the Lorentz transformed charge value are completely different for these Coolidge Hilbert spaces. And I mean, they are related by Lorentz transformations, but there's no notion of an infinitesimal Lorentz transformation, which, corresponds to the generator or angular momentum, because you're mapping between different Hilbert spaces and not within the same Hilbert space. Okay. So you found an S matrix, but your, Hilbert spaces now are not Lorentz invariant, and your states don't have any value of angular momentum or spin. Okay. The third problem, which is again the same problem, that you always have to send in this photon cloud. So this memory with even in the in state, if you want to work in the Faddeev-Coolidge Hilbert space. So any particle and antiparticle you want to send, if you want to put them in this Faddeev-Coolidge Hilbert space, you always have to send in some photons. Now you can hide these photons at very, very low frequencies, so it, doesn't register in your detector or something. Or your experimentalist friend doesn't notice that you put these in by secret. But this actually has a non-trivial effect, is you can actually show that this photon cloud completely decoheres the states. And this is not very straightforward to see, but what really is happening is the memory you have to send in to remain in the Faddeev-Coolidge Hilbert space depends on the momentum of the particles that you also want to send in, the electrons and positrons that you want to send in. And it is such that electrons with different momenta can never interfere, just because their photon clouds are completely orthogonal and completely decohere the state. So, if you want to send in a superposition, sort of a non-trivial entangled electron-positron pair or something, you cannot do it in this Hilbert space. It's a very strange Hilbert space, hopefully, even though I've explained that there's an S matrix for this Hilbert space. This is telling you to send in really strange states, and you really are changing the scattering problem just to solve it. And I also should mention here that this decoherence thing is not just a problem of sending in states, but this decoherence effect due to sort of photon clouds hiding at low frequencies actually happens in physical processes. And there's work by Dane Danielson, Satish Chandra, and Wald, which actually shows this. But okay, in massive QED, we can kind of fix all of these issues, but you kind of really have to very much generalize what Faddeev-Coolidge Hilbert spaces mean, and no longer is the original construction. But yeah, let me stop here if questions. Yeah.
So can you just show the last slide one more time? So I was trying to understand the statement about decoherence that you're making.
Yeah.
So so the point is that you cannot send in electron states with specific entanglement structure. Is that what you said, if I understood correctly?
Yeah. So each electron comes in with this photon cloud, right?
I see. And so, yeah, go ahead. Yeah. Please.
So yeah, if you can send in two electrons which look entangled just in the electron part.
I see.
But their photon clouds are completely orthogonal, so the total state is decoherent.
I see. Okay, thank you.
Yeah.
Yeah. Hi, I have a comment about that point. I think it was shown by Abhay many years ago in his lectures on asymptotic quantization that if you want Lorentz invariant scattering in massive QED, then the only scattering that is possible is trivial scattering. And I think that is consistent with the remark that you are making in your point number 3.
If you want to stick with Hilbert spaces.
If you want to stick with Hilbert space, that's right. That's right. So
yeah.
So if you so the scattering is completely trivial if you want to stick with the conventional notions of Hilbert space. That's right.
Correct. And I mean, Abhay was not working with Faddeev-Coolidge Hilbert spaces, but I mean, that argument also applies in his case. Yes, that is correct.
So let me. So does it mean that in this dressed Faddeev-Coolidge type Hilbert spaces, it feels like the scattering? Can you compute, for instance, loop level S matrix elements or something like that in this setup? Is it possible to do it?
Yeah, it is possible. It's just very complicated.
So
I mean, especially if you follow.
Yeah. So also, it seems to me that you also will have to specify the initial states in somehow more in more ways than we typically do, right? I mean, somehow the photons data also that we have to specify. The scattering is somehow. Yeah. Okay. I'm sorry that I'm interrupting so much, but I'm just trying to understand the overall picture. Thank you.
Yes. No, it's fine. No, I designed this talk for intermediate questions, so it's okay.
Sorry, I do have a question about, about something that Chetan just asked. I mean, if you wanted to do loops, then I thought it is only the out states and the in states that got dressed. We don't really know how electrons. Do we know? Rather, let me ask: do we know how electrons or positrons that run around in loops, how they get dressed?
In this picture, it doesn't matter.
That's what I thought. It's only the in states and the out states that are dressed, right, by the cloud.
Yes.
Yeah. So all that is happening in the inside is basically just controlled by standard QED perturbation.
Yeah. So then you would take off the dressing, get the compute your favorite scattering process, and then try to put the dressing back. If I understand this right.
Yeah, thanks. I think that comment helped me also, actually. Thank you.
Yeah. I mean, and you can do that if your dressing was sufficiently low frequency hidden, right?
That's right. It shouldn't, you shouldn't see it affecting the momentum state of your massive charged particle.
Yeah, but that's again up to some frequency resolution. If you go to
Yeah.
low enough
Yes,
frequencies,
yes,
you'll
absolutely.
always run into this problem. Yeah.
Yeah.
So yeah, I should
But
mention at this point
yeah,
that
sorry.
you can
I guess the
compute
point is that
things
you
called
can,
inclusive. Sorry,
yeah,
go
sorry,
ahead.
go on. No, go on.
Okay. I should mention here that, when you're doing scattering calculations, you can compute these things called inclusive cross sections, which are kind of already have a frequency cutoff baked into them, which is saying, my detector cannot detect, below nanohertz, so I'm going to ignore it. But those kinds of things you can compute, and you can also compute in standard QED. There's no problem. The real question is, what is the Hilbert space that you're starting from to compute the scattering?
Somehow the whole thing has a vibe that the flat space quantum gravity should somehow be thought of with an environment.
You mean QFT, not quantum gravity?
Yeah,
I
this
mean,
is just QED, right? This is
true,
just
but I'm
quantum
saying
electrodynamics.
but there is a there is a IR divergences, right?
Yes.
Yeah. So I would expect that, for instance, if you had like, I think you were insisting that the particles that you're scattering are masses. So I think if they are massless, I think things would be much worse.
Oh yeah, I'm getting to that also. But so let me comment on IR divergences. So the IR divergences come about because of this memory effect, but that we have already taken into account. So we have states that live in different Hilbert spaces. They look IR divergent in the standard Fock space, but there's nothing divergent about these states when you put them in their correct Hilbert space.
Oh, no, yeah, that's totally fine. But I'm saying that it's a physical fact that there is scattering that produces these.
Correct.
Classically, we see that there is memory effect. So somehow it has to be there in the scattering process.
Correct. Yes.
Can I ask a question in continuation of this very point?
Mm-hmm.
So if we were to calculate a scattering amplitude at certain L loop order, for example, so in that case, we would not encounter any IR pole if we are computing using this formalism that you are prescribing here. Is that correct? Am I interpreting it correctly?
You mean starting with Faddeev-Coolidge states?
Yes, exactly. So
yeah, you will not find any IR divergences. No.
But UV poles would still be there, is it?
Yeah, those are just a feature of quantum physics. I mean, you cannot get rid of singular UV behavior in any QFT.
Right. Okay.
Yeah.
And as you were saying, so once we remove the dressing from the in and out states, we get back the IR poles at the very end of our calculation. Yeah, I see. Okay.
Yeah. So the way this was, in QFT, discovered in QFT, is that you find all these IR divergences, and people realize that you can if you compute all the Feynman diagrams to all loop order or whatever, you can sum these up into what looks like a coherent state transformation. And that coherent state transformation is the thing I told you right at the beginning to construct these memory states. So it's the same effect. It's just seen in different ways.
Sorry, but I am not talking about summing up to all, like taking contributions from all loop orders. I am focusing on a specific loop order. Like, does the answer change in this regard, or I mean?
No, then in the Faddeev-Coolidge Hilbert space, you will not find any IR divergences because the memory is already taken into account.
Okay, that's what I wanted to understand. Okay.
Yes.
Yeah.
Okay. Now let's get to massless QED, which, as people have anticipated, is a ginormous problem. And this is not the most problematic theory in any case. So now if I make my electrons and positrons massless, so I'm sending in everything from null infinity. My electrons and positrons are also massless. They come in from null infinity. My photons come in from null infinity. And you can say, okay, good. Faddeev-Coolidge told us how to do that. So let's do it. So we set the charge at spatial infinity to 0. Now, instead of charges from time like infinity, which was for massive fields, because your electrons and positrons are massless, you get a current term. And this is given by some integral formula, but it's not really important what it is. And you get a divergence of memory, same as in the massive case. But if you fix a momentum, this current actually has a delta function in angles. So imagine a null particle going at some angle with, whatever speed or frequency that it wants to. The charge is concentrated only at the angle that particle comes out, and it actually is a delta function. So if you try to solve this equation, again, the zero here is just for convenience. You can put some finite function here. This is just the property of the Green's function of this equation. You get something that's 1 over angle minus the direction of the null particle that you started with. And you can see if they coincide, this memory actually diverges. The memory that you need to send in to construct your Faddeev-Coolidge dressing. And this is like a phenomenon of collinear divergence that shows up in massless QED all the time. Now, this wouldn't really be a problem if this singularity was sort of mild enough, but it's not. So you cannot square integrate this on a sphere. So it's not square integrable as a function on a sphere. And that has really drastic consequences, is that the dressing that you put on your massless positrons and electrons actually has infinite energy. The infinite energy is not in the electrons and positrons, but it's in this dressing that you want to put on them to put them back in this Faddeev-Coolidge construction. So all the states, if you construct a Faddeev-Coolidge Hilbert space in massless QED, all states except the vacuum have infinite energy. So it just fails in massless QED. You cannot do the Faddeev-Coolidge construction, and you don't have this preferred Hilbert space to do your scattering from. Okay, let's go one step further. Let's do linearized gravity. And here, actually, the situation is a little bit better. So the analog of this electric field, as I said, was this News tensor. And the gravitational memory is kind of the same, except, it has 2 indices, but it's symmetric, traceless tensor on a 2-sphere. And you say, okay, let's try this case, and let's try to do the Faddeev-Coolidge construction again. Now, here you run into kind of a technicality that you cannot set so here the charges are kind of analogs of energy and momentum, but at different angles. And these are like the charges associated to the BMS group. And that long story I won't go into right now, but the L equals 0 piece is the energy. The L equals 1 pieces are the 3 momentum. And all these extra charges come in at harmonics greater than equal to 2. Now the energy and momentum you cannot set to 0. So let's set the extra pieces to 0. And in this case, if you look at the conservation law, you get 2 derivatives of the gravitational memory. I'm not telling you how all of this is derived, but trust me, this is the formula. And this T is kind of some stress energy flux of some matter sources, massless in this case, that you've been sending in. So again, you can think of these as electron positrons, but now this is some stress energy term instead of the electromagnetic current term. That also has a delta function behavior at fixed momentum. But because your equation now has 2 derivatives, the singularity is actually not there at all. And it is obviously, it's L2 because it's not singular. And the dressing now has finite energy. So in linearized gravity, you can construct the analogs of the Faddeev-Coolidge Hilbert space by gravitationally dressing your massless fields. And that is allowed. There's no actual problem with the energy being finite. But you run into sort of familiar issues with these Faddeev-Coolidge constructions is, choosing a value just for the higher harmonics is not Lorentz invariant. So if you boost it, you'll get something non-zero if you started with 0. So you again don't have any notion of angular momentum or spin for these kinds of states. And now full gravity comes into the picture and just throws everything out the window. So a lot of things don't change. The memory formula and all that is the same. And now I'm not putting in any matter. So this is pure gravity. But what happens is gravity acts as a source for itself. So the square of this News tensor gives you an extra contribution to the charge. And then you again have the two derivatives of memory. So this should be familiar if we also integrate over angles. So we pick the L equals 0 part of News squared. That's the Bondi mass formula. So that tells you the energy loss. This formula is just a generalization for all these angle-dependent charges. And in this case, you can still construct these Hilbert spaces of infinite memory. But again, memory is not conserved, so you shouldn't do that. But gravity kind of sources itself. So if you try to dress your graviton, so if you try to put in memory, so if memory is non-zero, the News must be non-zero, but that will also contribute to this term. And then you have to dress it again and again. Hopefully, you can hope that maybe you can end this at some finite place. But we showed a theorem that the only Hadamard state, Hadamard is kind of a mathematical condition on the UV singularities that ensures finite energy of your state. But the only eigenstate which has a fixed value of the charge is the vacuum, whose charge is 0. So, and the vacuum doesn't do anything. So there is no vacuum state in any Faddeev-Coolidge Hilbert space, no non-vacuum state in any Faddeev-Coolidge type Hilbert space in nonlinear GR. So if one was hoping that, Faddeev-Coolidge gives us an S matrix for massive QED, hopefully, it doesn't work for massless QED, but that's a bad theory. It works for linearized gravity, so maybe it'll work for nonlinear GR. It doesn't. It completely fails. And if you really want to follow Faddeev-Coolidge, the only thing you can send in is the vacuum, which is the best state, according to Faddeev-Coolidge, because that's the only Faddeev-Coolidge state. So that's the issue. All of these are the things I basically said. The real problem with all of this is that we're saying that we want all our states to live in one Hilbert space or a collection of Hilbert spaces. And this is, usually how we do QFT, how it's taught in textbooks. So you start with the Hilbert space, you do all that. But really, there is a huge supply of states. By states now, I just mean that the operator algebra is completely fine. None of these infinite things show up in the operator algebra. And you can define states just in terms of correlation functions of operators. So if you give me a list of correlation functions of all operators, then that defines for you a state. So there's a huge number of states. It's just that you cannot force all the in and out states that show up in scattering into one Hilbert space. That is not possible. And this, is familiar. If people do QFT in curved spacetimes, you run into the same problem. You just cannot put all the states into one Hilbert space. And a similar problem now is showing up even in scattering in Minkowski spacetime. So for example, in massless QED, the Faddeev-Coolidge thing didn't work, but there's still a huge number of states. They just don't all lie in Faddeev-Coolidge Hilbert spaces or one of this memory Hilbert spaces or anything of that sort. So I'm claiming we should give up on Hilbert spaces. We can still do scattering. And I'm going to sort of explain how to do it. If you ask me how to actually compute it, I will say, oh, we're working on it. But you specify your in and out states as list of correlation functions. So here, omega is now a state, not a frequency. What this is saying is that the state is specified by correlation functions of all its operators. So whatever operator you constructed at infinity, you would include in this. Now, given any state, I mean, this goes by the fancy name of algebraic state, but if I say algebraic QFT, people kind of stop listening. So I'm just going to call it correlation functions. So given a list of these correlation functions, so one list, so one state, you can always make up a Hilbert space in which it lives. But you cannot demand that all possible states live in a single Hilbert space. So this is kind of analogous to, in gravity, sometimes you cannot stick to one coordinate system. Given a point in space-time, you can find a coordinate system in which it lives, but you cannot say, oh, I want all my points to live in the same coordinate system. I mean, that's not even true on a two-sphere, forget gravity. So this is kind of similar to that. You have a bunch of states. They all live in different Hilbert spaces. Let's just deal with them. So that's the proposal.
Karthik, I just have a question. So if I had because in the earlier slide you said that one has the full algebra, right?
Correct.
No problem with the algebra of operators, whatever the C star algebra that you have.
It's a star algebra, but yes.
Star algebra, okay. But then in that case, you often think of one thinks of the state as in terms of a representation of that algebra, right?
No. One thinks of states as algebraic states in these correlation function terms.
Yes, but
once you're given that, you can do what's called a GNS construction and put it in a Hilbert space that is a representation of the algebra.
Yes. So what I'm trying to say is that if it is a representation of that algebra, then there is that particular carrier space, that Hilbert space is what you it's just a representation of that algebra. But
it doesn't include all states. That's my point.
Now the question is, so the statement about all states seems to then be a statement that is beyond this operator algebra. Is that right? Because that's what I'm not fully understanding. If the algebra is, because if you have the full algebra of operators, then you have the representation of that algebra
on some Hilbert space, but there are many inequivalent Hilbert space representations of the same algebra.
Right, yeah. Of course. But within any irreducible representation, you will stay within that representation by any action of these operators. But of course, I guess the point that you're making is that the scattering is not one of these operators.
Correct. The scattering does not map you from, so for example, this construction is what gives you the zero memory, the memory Fock spaces. Right. It's exactly the GNS construction, and those are not preserved under scattering.
Right. So somehow it is not, the scattering state is not a scattering operator. It's not part of your initial
operator algebra. No, it's not. You have to find it.
Right. But it's something that we want to still attribute physical meaning to. So one then needs to, correct. Right. Okay. Thanks.
So maybe I can say something, and I don't know if it's relevant to what Sumati just said, but the states that you get when you look at it from the operator algebra point of view, the Fock state is only one of the possible states. Most of the states that many, if not most of them, are non-Fock representations. Correct. And if I were to interpret Fadim Kulish sort of loosely, then they are halfway between Fock and non-Fock states, and there are some advantages and many disadvantages to working in that way. The number of photons that they allow to be an unbounded number of photons. So in that sense, the photon part is non-Fock, but they are looking at massive charge particles. They have finite number of massive charge particles. So that's where the state is Fock-like. So I don't know whether this is one of the reasons why they can make some progress, but there are also the difficulties that you pointed out.
Yes, no, that I 100% agree with that. Is that the photons are non-Fock. So, the quote unquote particle number really is infinite. So they can make some headway into including memory states. So states with memory, usually you will see these as described as they have infinite number of soft photons or something.
Yes.
But that's just a very crude way of saying that they live in a different Hilbert space.
That's right.
Yeah. Which is exactly why Faddeev-Coolidge in the massive case works to some extent at least.
Yes.
But then completely bombs in other cases that you want to consider.
And I think this requires actually a rethink. Perhaps you are also suggesting it. This requires a way for us to rethink and to start loving non-Fock states and treating them with more respect, which until now we haven't really done it, except in some very limited circumstances like phase transitions.
100%. That's exactly what I'm saying. We should do it in QFT.
Please continue.
Yeah. Okay. So
thanks for that, Karthik, because I think in one shot you clarified also this thing about soft photons for me. So thank you very much.
Great. Okay. So let's go with this idea of we're just considering, we're not going to a priori say, before we do the scattering calculation, we shouldn't decide, I want my outstate to live in the same Hilbert space or some Hilbert space that I randomly chose. I mean, you don't get that choice. You get a choice of sending in an in-state, whatever you want. Then the scattering and the dynamics takes over and gives you whatever outstate it gives you. It doesn't care about your preferences for Hilbert spaces. Okay. So what would scattering in something like this look like? It would be given by, instead of S, for S matrix, I'm writing $. This is like a notation borrowed from Hawking's earlier work, but kind of modified a bit. So it's a map. And this is completely an abstract definition. And if you ask me how to calculate this, that's a legitimate question. I'll mention a few things in a bit, but it's a map. So given an in-state, it gives you an outstate. I mean, this is the most basic thing you can ask from scattering without assuming Hilbert spaces. And again, the in and out state omega, not frequency omega, state omega, I mean in terms of correlation functions. So you give me a list of correlation functions of the in operators. What this dollar map does for you is it generates the correlation functions on the future, the out operators. And you can formulate conservation of probability and what information loss looks like in this dollar map. The question is how to practically compute some map like this. And the problem is the usual QFT textbook scattering calculations don't work, because the way they usually do is you assume all states can be generated from the vacuum. So they're in the standard Fock space. Then there's this LSZ reduction formula, which basically tells you all the S matrix elements can be computed in terms of Feynman diagrams. And you compute Feynman diagrams to, 536th order, if you like, get some answer. But this doesn't work because you're starting with the assumption that the only states are Fock-like. And that is just false in this situation. So this is ongoing work with Gautam Satishchandra on how to actually calculate this, at least to some finite order in perturbation theory, which won't handle the full gravitational case yet, but we're at least trying to make some headway in the other cases where Faddeev-Coolidge doesn't work. And the idea is that, as I mentioned, the operator algebra is completely well-defined, and operators have a well-defined Heisenberg evolution. So we're not working in the Schrodinger picture. We're not working in the interaction picture, which, kind of is hand-wavy anyway. But let's work in the Heisenberg picture where the operators satisfy the field equations of the theory in operator form and try to compute how, given an in-correlation function, so correlation functions of some in operators, can I evolve these operators all the way to future infinity to get the outstate? And again, this probably will be done to some finite order in perturbation theory, but I don't want to give too much away on what we're trying to do, but it's a work in progress. And that's my talk. Thanks.
So thanks, Karthik, for the wonderful talk. So are there any questions? So Sumati has raised a hand.
No, sorry, I wanted to clap.
Okay, okay.
I put the wrong. I mean, I do have questions, but I wanted to clap. I'll wait
Okay.
for it.
Okay. So yeah, please feel free to ask the questions.
Okay. Can I ask a question? I mean, I have to raise my hand, I guess. Okay. Gaurav, shall I go ahead?
Yes, yes, sure.
Oh, okay. So in the last slide, you mentioned in operators and out operators, as well as in states and out states. I mean, the operator algebra should be an identical algebra for the in and out cases, right?
They are isomorphic, yes, but the evolution
description at the level of choosing different states for in and out, or at the level of different states. That's my confusion here.
So the difference, okay. So the difference is the following. So the operator algebras are isomorphic in the sense that you can pick a map between them. So you can say, the past electric field operator is the same as the future electric field operator. That's a choice. That's not the scattering map. If you actually evolve the operators, it won't remain the same when there are interactions. So time evolution is still an isomorphism, but it's a different isomorphism than just identifying them directly.
Right. But my question is, do I also pick different states when I evaluate the correlators at, say, minus t going to minus infinity and say t going to plus infinity?
Yeah, okay, I understand the question. So let's work in the Heisenberg picture, right?
Okay.
So we'll evolve the operators. We won't evolve the global state.
Okay. Okay.
Right? So the Heisenberg state remains the same, but the operators change around by evolution.
That's fine. Yeah, I mean, you were using both words, so I got a little confused there, actually.
Okay, yes, sorry. So what I mean by in state is you take your Heisenberg state, which is a global state, but only compute. So when you compute correlation functions, all the operators are in operators. And what I mean by out state, I mean, here I really mean in and out in terms of correlation functions, not Heisenberg picture. I think that was the confusion. So out state is compute the Heisenberg state, but put all the out operators in the thing to compute correlation.
That's clear. Yeah. Yeah. Then it's okay. Yeah.
Okay.
I was wondering whether this permissurance question may be related to this point that not all automorphisms of a non-commutative algebra are inner. There are interesting outer automorphisms also.
Yes.
If it's an inner automorphism, then you can realize it via a straightforward unitary operator. Outer automorphisms are more subtle to implement, right? So maybe that is the way to think about this dollar map, that the algebras are isomorphic, but they are related by an outer automorphism.
I mean, so one thing is, even if dollar is an inner automorphism, you can write it as a unitary, but that unitary need not be implemented as an operator on some specific Hilbert space. So even if dollar is an inner automorphism, there can still be non-trivial scattering maps.
Right. I think that might that doesn't contradict the fact that the automorphism under question may be an outer one.
It may be, yes. I agree.
Because for example, the automorphisms that change the nature of the state that we think of as affecting the behavior at infinity are often outer. Like boost or automorphisms. Yeah, that's right. Boost is an example of an automorphism, which is an outer automorphism, right? Especially because it changes the nature of it changes the amount of energy that you see at spatial infinity.
Yeah.
So it's not, you cannot realize it as a local. First of all, you can't realize it as a local. You can't construct it from a local. You can't do it locally.
Yeah.
Right. Okay.
But in this case, anyway, it's not just local, right? Because you're time evolving way of Heisenberg equations. So you have Hamiltonian, which is not a local operator. Right.
That's right.
Yes.
You have to.
Can I ask a related question? So let's say you're able to calculate all the correlation functions and you have some answer, but I still have to translate that into some cross section they can measure at LHC or whatever, right? So how would you envisage doing that? By factorizing the correlators into some kind of extracting some momentum eigenstates out of that? Is that how you're thinking?
Yeah, so momentum eigenstates are a problem because momentum eigenstates are a basis for the standard Fock space,
right,
not for all these other Fock spaces.
So how do you envisage the map from correlators to an actual, say, cross-section?
Yeah, so the actual cross-section, you can rewrite an actual cross-section as probability distribution of some observable, some operator in your algebra. Even in standard QFT, that's how you calculate them, right? So I think something of that sort is happening, and it really is, you say, so the correlation functions that I compute, I don't put in this memory thing in my operators, because that's something I cannot detect at finite time in LHC, right? That's a zero frequency, infinite time effect. So if you compute correlation functions of, say, the electric field, that will correspond to a probability distribution of the electric field on different values that it can take. And that should translate to something like a cross-section that you can observe.
Okay. Yeah, thank you.
Thanks.
So maybe I'll just make one comment about I think so you are trying to work with massless particles together with QED. So there are these claims which people make about things called weak gravity conjecture, etc., which basically puts bounds on whether the charged particle can have, how weak they can be. And I think this seems like something that might be a massless charged particle, at least in theories with gravity, is ruled out based on some heuristic or, let's say, stringy arguments and so on. So
here we're not trying to couple it to gravity, right? We're just doing massless QED without coupling it to gravity.
I understand. I'm saying that if you wanted to ever couple it to gravity, and since the world contains gravity, such a theory would be ruled out. So it's in the same sense that, for instance, theories which are gravitationally anomalous, you expect they're not consistent, in the sense that, they're not, if they're consistent, if you don't couple it to gravity.
Right.
So
I'm just saying that's a higher order problem, right? We're kind of addressing, is scattering well defined when you turn off gravity?
Yeah, I'm just saying that, in a world which contains gravity, there might be reasons why anyway it is not standalone. Yeah.
Sure, yeah, that is possible. Yeah.
Are there any other questions? Okay. So thank you so much, Karthik. It was a very interesting talk, and as you can see, there is considerable interest in the kinds of things that you have told us. So let us please join me in thanking Karthik for a very clear presentation. And I will say goodbye now, and we will see you for the next GGHAT meeting. Thank you, everyone.
Thank you.
Yeah, thanks, Karthik.
Thanks, Karthik.
Thank you very much.
Thank you. Thank you very much.